go over the very first beginning of beams quickly, and then we'll get into some more advanced topics. Now, this is truly a topic that you should have seen previously. Nothing I'm going to show until late today should be new. Nothing. And even then, it'll be one new thing, and then there'll be some more review. Okay, so but this is stuff that you should know. Now, when we talk about beams, we commonly talk about, and we thought about, or at least as undergrads, we thought about charts that look something like that, where we had a zone 1, a zone 2, and a zone 3, right? And what kind of failure mode happens in zone 1? Elastic hinge. Zone 2? Inelastic lateral torsional buckling. Lateral torsional buckling. We'll talk more about that today. In zone 3? Elastic lateral torsional buckling. Great. The key variable. This was moment up here, and this was, what's LCB? Length between the braces. Length between the braces. There's LB1, LB2, and LB3. Okay, looks something like that. We have to remember that if we had a problem that looks something like this, where the X's are braces, and we typically assume that every one of our end connections is a brace, typically, it's assumed that they're a brace, then you have to look at a moment and an L sub B, and possibly a C sub B, for those that remember what that is, for every single one of these segments of beam. Okay? Okay. So we're going to first talk about plastic hinges. Okay? We're first going to talk about the first part of the snail chart right here. Okay? And we're going to, by the way, I just want to, it's always good to talk about where we're going, right? Where we're going, and we've, as undergrads, we dealt with a single snail chart, right? A single snail chart, and we dealt with only rolled sections. Okay. Now, if you have rolled sections and single snail charts, are the way to go. Totally the way to go. If you have built-up sections, then we're going to find out we're going to have to deal with the 4 snails of apocalypse. You've heard of the 4 horses, right, of apocalypse? You've got the 4 snails of apocalypse, right? And this is only one of them. Okay, and there's 3 more coming, right? That's my name. You won't find that in any textbook. Okay, believe it or not. You know how cool it is. Yeah. So Halloween's coming. Snails are scary. I figure it's the same. So anyway, we're dealing with 1 snail. And we're gonna introduce another one coming up. Okay. Then we're gonna introduce a third. Then we're gonna introduce a 4th. All right. So ultimately, you're gonna be dealing with the 4 snails. Okay. Right now, we just know 1. And the other ones won't go away. They're just going to be supplemented. We'll understand. Hopefully that'll make more sense today or on Wednesday. Now, when we talk about members and plastic hinge formation, all these notes are basically telling you down here is they're saying, remember that when we very first took structural analysis, we were very comfortable with MY over I being the stress. Right, and then as we introduced this type of concept in the steel class, or at least in my steel class, maybe you saw it some in reinforced concrete as well, that when things actually start straining above the yield strain, life is not over. Life does not stop. You are able to these materials are able to go beyond yield, and that's structural resiliency on a cross-sectional type level. Right? On a cross-sectional type level. And then I have this handout on the other side that it explains it. And again, if you've seen this before, bear with me. If you haven't seen this before, then pay attention, because I'm going to have to cover it a little bit faster than I usually would. Because a majority of these people have already seen this type of stuff. But if I show a beam and I have loads, and I'm talking about the center of the beam. Okay, we're talking about the center of the beam and all of these things that we're talking about. And this is the cross section. We're just going to pick rectangular because it makes life easier. And I have 3 spots. Spot 1, spot 2, and spot 3. Spot 1 is on the extreme fiber. Spot 3 is on the neutral axis, and spot 2 is in the dead center. And I'm saying as I load this up, and I'm going to have some kind of strain. It's going to look something like that. This is before I get to yielding. Okay? And I'm going to have stress that corresponds to that strain. If I know strain, how do I get stress? I know it's a Monday. I have strain. How do I get stress? That's right. Multiply by Young's modulus. Hooke's law, right? Hooke's law, right? That's exactly right. Multiply this by E, and I get this. Okay? And I'm telling you all my loads, and I've got some lines drawn here on the yield stress, and everything's below the yield stress. So now I'm drawing this cross section where things are at on the stress strain curve. That's a little bright. Dial that down a little bit. Come on, baby. There you go. There you go. Okay, so everything, point 1 is the highest strain, point 2 is in the middle, and point 3 is 0 because it's the neutral axis. Get with me. Yes? Low loads, everything's elastic, that's how it behaves, that's how it works, that's what it's all about. Now as I start increasing the loads, I put W2 on it, and W2 is more than W1, and I increase the load until it yields. Until it yields at the extreme fiber. This is the amount of yielded material. This little bit is yielded right there and right there. Oh, my strain is at yield here. Oh, my stress is at yield here. And oh, point 1 is right there. And everything else is below it. Is life over? No, because I got so much more of a page, right? And well, we've been talking about structural resiliency, and we know that no, that can't be the way it is. We have to live on. So we got load number 3 now, which is higher than load number 2 and load number 1. But how can that be? Because now my yield is above, my strain is above the yield strain. Wow, that can happen. And look, my stress is above the yield strain, but hey, it's flat. Why didn't my stress keep going up like it did here? Why didn't my stress keep going? Why did my stress go higher? It's because what? Because it yielded. It's because I'm here. It's because, remember, the stress strain diagram says that, you know what, Steele? You're not allowed to go any higher than that. At least not until you strain harden, right? And then we go back to why didn't we fail? And that answer is structural resiliency, right? Why aren't we dead? Because number 2 says, I'm not ready to go out yet. Still got some fight in me. And 3 says, I'm not even close ready to die. Like bring it on, sucker. Okay, so they keep going. That's a technical word, sucker, right? So they keep increasing the load, Okay, we get more of it yielded. More of it yielded here. More of the cross section's above strain. More of the cross section is at its yield. Oh, so much until point 2 has now reached its yield. But life again is not over. It's stressful, but it's not over. Not over. We can keep increasing loads. Keep increasing. Now all of this is yielded. All of this is what our strain looks like. This is what our stress looks like. Well, we're getting pretty bad now. It's getting pretty high up on the hill, but it's not dead yet until the entire cross section is at yield. Everything is at its strain, as its rotation. Everything is at its stress. Boom, like something like that. Can we go further? Why not? What's that? It's going to deform. How come? It's plastic. Okay, that's a good answer. Let's do a more basic answer. We said it turns into a plastic hinge. What does hinge mean? Lost all of its stiffness. It's lost all of its stiffness. Okay? That's what's going on here. Actually, as we shade this, that's the only part that has any stiffness left. That unshaded part. Same thing here and same thing here. So the whole time, if we were to plot a moment versus curvature, and curvature is this internal angle in here. Okay? This internal angle is the curvature. If we were to plot our moment versus curvature, we'll find that it's stiff, but after W2, actually after W1 it loses a little stiffness. After W2 it loses a lot of stiffness, then more stiffness, then more stiffness, then more stiffness. It's losing stiffness. It's losing stiffness. Okay. Is stiffness important? If you want to hold things up without large deflections, then stiffness is really important. Really important. Okay, awesome. So we talked about this before. There's a couple things you've seen before. Remember talking about the S? What's the equation for S? What's it called? Section modulus? What's the equation for it? Do you remember? No. I over Y. Thank you. And remember, it's the I over Y that creates the largest or smallest S. Smallest S. What this is really about is S tells you when yield happens. It tells you when S times F sub Y. So you may have a cross section. I love to do this. I love to do this. Put like a T shape. And you'll actually have two different S's. An S for the top and an S for the bottom. So remember that the true S is going to be the one that corresponds to the yield moment. So if everything is a constant yield strength, then that'll be the one that's closest, the smallest Y, because I is constant, right, for that cross section. Okay, we're about to venture in the world of non-equal yield stresses on cross sections. Why would I do that to you? Well, because you need to understand it if you're a graduate student, and someone may do that to you someday. They may do like a hybrid girder. They put really, really high strength material in the flanges, low strength material in the webs. It was like really sexy to do that about 5 or 6 years ago, but it's wearing away. Sexiness is wearing away because they realize that stiffness is no difference. It doesn't change stiffness. Anyway, but then we're going to introduce something called Z, which is the plastic section modulus. And the definition of Z is you take Fy, you multiply it by Z, and you get M sub P. And the great thing is in the past, you've always had Z's given to you in the manual, right? And if you had me for an undergraduate class, I made you calculate Z's. You're going to have to do it again. And now we're going to learn how to do it if there's not a uniform yield on the cross section. Okay? That changes things a little bit. All right? All right. So we got M sub P. And remember, there's no phi factor, but there is a phi factor typically. What's phi in bending? Who remembers? 0.9. Good. 0.9. And we have something we're going to call the shape factor. And the shape factor is the ratio of M sub P over M sub Y, or Z over S. Now, this works great for a uniform yield. But guess what? In this class, we're not going to have uniform yield strengths. This won't help you. You're going to have to use M sub P over M sub Y. Okay? M sub P over M sub Y. And remember, what's M sub Y again? It's the moment when yielding first happens. What's M sub P? The moment when the plastic hinge forms. Go back to first principles, go back to the basics, and you'll get them all right. Okay? Okay. Any questions on this? Awesome! Now, the cool thing about the shape factor is it actually depends on what the cross-section. Again, this is all assuming constant yield stress. Okay? We don't have a constant yield stress. Everything goes out the window. Okay? But remember, the shape factor is pretty cool because it's just about the cross-section you use. It gives you the ductility. The ductility. It's a measurement of ductility. Well, that's what ductility is, right? The area underneath the stress-strain curve, right? The area between the amount of extra you have between first yield and ultimate plastic failure. The cross sections actually will give you different ductility. Well, that's kind of cool. So if that's the case, then actually in ductility, I say, what is ductility? Hey, it's the amount of material underneath the stress-strain curve. ASCE limits the shape factor of a section to 1.5 currently. And then I ask the question, why? 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 Why would we limit our shape factor? Why would we limit our ductility of our cross-section? Ductility is good. Why would we limit it? Why don't we have diamond-shaped beams? They are. Well, whenever the middle, say that again, whenever the middle yields.
Because there's so much amount of thickness right in the middle instead of like you did by the shape.
You're definitely on the right track, Jacob. You're right on the right track. You're really close. And what I'm going to say is that if we look at, basically, if we look at stiffness is a good thing. Stiffness is a very good thing. If we don't have very stiff structures or stiff whatevers, as you're using it, it would be all floppy around. Imagine trying to write with a pen that wasn't stiff, right? You go to push on it and go, it like scrunches on you, right? And you go and you're writing it bends on you, right? It wouldn't be very useful. Wouldn't be very useful. Imagine writing on a desk that wasn't stiff. Like as you're writing on it, it moves. Okay? So there's a lot of things. I mean, it didn't break, but there's a lot of benefits of having things that are stiff, plenty stiff. Okay? Now, what goes on here is exactly what you're saying. There's so much material around the neutral axis here that this diamond is going to start yielding pretty early in its life. Right? It's going to start yielding. So, diamonds may be girls' best friends, but not engineers' best friends. Okay? Not structural engineers' best friends. Okay? Because it may start yielding right here. And what does yield mean? Loss of stiffness. So if you start, as you're loading, you start losing stiffness, then you would have a structure that would have plenty of ductility, plenty of bend but don't break type attitude, but it would be kind of flexible, right? It would be very flexible. It would move a lot when it's loaded. It would be something that you would start using it and you would start yielding it pretty early and say, oh, don't worry, it's not going to fail, but it may become springy. Okay? It may become more flexible, more bouncy. Prime test question. Okay, we got round, we got rectangular, we got tube, and that's one reason why AISC cuts it right there, is because it comes down to serviceability. It comes down to we need to provide structures that are very serviceable. And we don't check for a lot of these serviceability limits. We do things like live load deflection limits. Okay, that'll be coming up. And we do things like this to keep us out of doing hardcore checks on, okay, well, what's our typical loading we would put on that? Okay, well, how much yielding would happen on that cross-section? What would be typical deflections? We don't do that. We don't ever do that. These are the things that would help us stay away from that. Any questions on that? Okay, so we talked about that. That's cool and all. We talked about calculating the plastic section modulus, and I'll cover this. I go, let's start by talking about this section modulus. That's S is equal to I over Y. Plastic section modulus is a little different. Let's look at stress diagram for a beam that's at a plastic moment. Okay, basically we find this point of equal area. Now this is only for, please write yourself a note, this is only for a constant yield strength. Okay, we don't have a constant yield strength, which we won't in this class. You're going to have to work things a little differently. But what you do is we'd find the point of equal area. We would plastify everything above that point, plastify everything below that point, find the resultants for each one of them, and sum it about the moment. Right? It's pretty easy to do if it's a rectangle. There's the equation. That's all we're doing here. This is the resultant was P. X bar is the moment arm for each one, and we have to plastify it. So if we have something that's more complicated, like a I shape, for example, then when we go to do this, the point of equal area, that's easy. That's the center, right? We're going to have a resultant from where we plastify the top, where we plastify the web, where we plastify the other web, where we plastify the other top. We have to find moment arms for each one of these. Not that hard, not that bad. Easy. That was undergrad stuff. Okay, for doubly symmetric members with constant yield stress, the centroid is equal to the point of equal area. But that's doubly symmetric. Those are both doubly symmetric. If I go singly symmetric, like I'll go on the single page, we've got to find the point of equilibrium, not the centroid. But again, Z is equal to M sub P over Fy. Okay, there's some math. I'm not going to go through this. You should be able to do this on your own or have seen this before. I give you a cross section. I find out what S is. Then I find out what Z is. Okay, and I calculate the shape factor. And oh boy, I got 1.5. That's the same thing I showed you on that previous table, previous graph, 1.5. Great. Then I say let's up the game a little bit. Let's show a T shape. And oh yeah, I tell you in this class, there is no partial credit in this class for centroid calculations or for moment of inertia calculations. No partial credit. They're either right or they're wrong. Okay, so get them right. Okay, so you find the centroid because that's what you need to get y. You find the I, and for the y calculation, you find the s. Great, awesome, easy, no big deal. Now we got to find z. In this problem, it was the point of equilibrium. Why was it the point of equilibrium? Because it was a constant yield strength. You with me? Okay. Find the point of equilibrium. Again, if the yield strengths are the same. Underline that. So then I found the area of the top flange. I find the area of the bottom flange. I call one of it x. And I know, therefore, that it's in the top flange. Look at this. I found the area of the top flange. I find the area of the bottom flange. And I want them to be equal. So I have to take away from the top flange and give it to the web. Take away from the top flange and give it to the web. Right? So I know I'm going to call this distance x. This has to be 3 minus x. And I already know what this depth is. It's like 17. Do a little algebra here to find out what x has to be. It's 0.28x. I go ahead and check myself just to verify that I get the same value, and I do. Okay, so 0.28x. Where did I? Is that the last page? Let's see here. Boom. Oh, yay. Next handout. Okay, so I found my 0.28x. Now all I have to do is find my z. So I have to classify my cross-section, find my m sub p. I found that. That's a little sliver from the top flange. That's the little sliver from the bottom part of the top flange. And that's from the web. Easy. Cake. No big deal. Old stuff. There I'm calculating m sub p. Okay, so summing all these up. That's for p1. That's for p2. That's for p3. I find m sub p. I take z. Z is m sub p over Fy. Find 351 inches cubed. I calculate my shape factor. I get 1.8. Let's see. Was that on that table? Nope. Wasn't. 1.8. And that's the shape factor you get when you have T's. Typical T's. T's that have similar proportions. Okay, great. Yawn. Boring. Old stuff. Let's do new. Woohoo! What if we use steels with different yield strengths? What if we use steels with different yield strengths? Okay, so let's see. Get my. Now I say that all of the S, I, and Y bar calcs are the same. I don't know if that's totally true. I mean, the traditional calc for Y bar is the same. The traditional calc for I is the same. Now, I doesn't have any impact on yield strength. It doesn't change because of yield strength. If the modulus changes, it can change. But remember, we're lucky we're dealing with steel. It's always 29,000 KSI. Okay? At least with this deal. Y bar doesn't have any impact on yield strength, but what is S? What's the definition of S? It's not just I over Y. What's that? No, that's the shape factor. S is the section modulus, which is traditionally I over Y. But there's a more refined graduate school-y way that you need to look at it. Well, I'm going to tell you that in this class, you need to retrain yourself. That when you think of S, it needs to be, that's the equation. My equals S times Fy. And when Fy is constant, then S is truly equal to I over Y. But in this class, it's very possible that I could give you, let's say I give you an I shape. It's really tall. And let's say I make these 100 KSI. And let's say for fun I make this 4 KSI. What's the definition of MY? When first yield occurs. First yield occurs. So where do you suspect first yield is going to occur on a problem like this? In the web. Well, I'm going to say that's neutral axis. You agree? If they're all symmetrical, they're all the same numbers. That's the neutral axis. We know the stress is going to want to look something like that, right? Right? So we're at in the web. Which one? Both. They happen at the same time. Happen at the same time. Phone was excited. This happens here and here. Okay? So now, to find out what M sub y is, you can find out how much moment it takes to make that happen. You with me? Depending, I could change this. Let's say I make this 40 KSI. Let's say I make this 100, and let's say I make this 60. Now where? Well, now I don't know. Could be here. Could be here. Here, these are still both the same. It could be here. I could start changing flange widths. I could play all kinds of games. And you start to say, well, you check. What if is this one it? Is this one it? Is this one it? You have to check maybe all 4. And figure out which one to control. Which one is going to control? The lowest M sub y. The lowest moment. And that's going to be your M sub y you use. So when you start to talk about S in this type of calculations, S starts to break down. The classic meaning of S, of I over Y, but they didn't lie to you, but they didn't tell you the whole truth because they didn't want to melt your brain when you're first taking strengths because they melt your brain with other stuff. That you need to change. You need to change. S in these hybrid shape girders, hybrids ones with different steel stresses, classic definitions start to change. Instead you start to talk in M sub y's and M sub p's. With me? Okay? So if you don't ask a question, then I can't help you get an answer. So, onward we go. So, the S, the I, the Y are the same. Well, the I and the Y are the same. The S is different. M sub y, we talked about how to do that. But the plastic neutral axis and M sub p calcs are totally different. the previous examples, we found the point of equal area. Now we have to find the point of equal load. The point where the area times the yield strength. The summation of the areas times the yield strengths have to be equal to 0. Why is that? Because there's no net axial load on the member. So summation of forces into the page have to be 0. They have to be 0. Not it'd be flying through space. Right? Or it'd be an axial load column. Okay? So the sum of the areas times f sub y has to be equal to 0. We do this because there's no net axial load on the specimen. Now, so let's work the problem. So in the past, what we did, we took the area of the web when compared to the area of the flange. Can't do that now. You have to take the area of the web times f sub y, compared to the area of the flange times f sub y. Now, here's my cross section. I've got 100 ksi, 36 ksi, 14 by 3, 17 by 2. Okay? So, here we go. Area of the web times fy. Well, that's going to be 17 times 2 times 100. That's 3,400 kips. Is that a lot of load? It's like 170 Toyota Corollas. It's a lot of load. Okay. Flange. 14 times what? 3 times what? 36. 15, 12 kips. Okay, so what's this mean? What does it mean? We want these two numbers to be what? Equal. So how can we make them equal? Reduce this one and increase this one. How do we do that? Take area away from the web, give it to this other area, right? So I know that I want to take area away from the web and give it to the top. I know that my plastic neutral axis is going to be somewhere in the web of my member. Okay, so now I do something similar to what I did before. I'm going to take the total area of the flange, 14, actually not the total area, the total component. Right? That's the same as 1512. It's the same. Just going to write it out though, so it's all clear. This is the flange. The flange contribution. And I'm going to add to it 2-inch width. X is my depth. What's my yield strength of my web? 100. And I want to set it equal to 17 minus x times 2 times 100. I want to solve this. 1512 plus 200x equals 3,400 minus 200x, 400x equals 1888. X equals 4.72 inches. What's that mean? That is the distance from what? From there, right? Distance from the interface between the web and the flange, that distance is 4.72. So if I want to find this magical distance on my cross section, it's 4.72 plus 3, which is 7.72 inches. Okay, am I done? What am I trying to find? What's my goal? found m sub y. What's the other one we usually look for? M sub p. We're trying to find m sub p. So what do we do now? Well, we found our plastic neutral axis. We plastify everything above. We plastify everything below. Figure out the components, multiply by the moment arms. So let's do that. M sub p. So again, 3 times 14 times 36. What's that for? That's right. What's that? I have to multiply it by a moment arm. 7.72 minus 3 halves. Why is it 3 halves? It's half the distance, isn't it? Plus 4.72 times 2 times 100 times 4.72 over 2. Okay, 4.72. Well, that's that little chunk. 2 is the width. 100 is the yield. 4.72 over 2, that's the moment arm. Great. 12.28. What? That's that area below. Times 2 times 100 times 12.28 over 2. That's the moment arm. 26,712 kip inches. Okay, let's say I want to find my shape factor. What's that?
Is that third part added?
Yes, thanks. Yes, they're all have to be added together. Appreciate that. Shape factor. How do I find a shape factor? What is a shape factor? MP over my. And that should be the answer. It's not Z over S anymore. Okay? It's not Z over S. Now when you don't have the uniform yield, it's MP over my. So that's 26,712 over whatever my is, and we didn't calculate it for this one. We could, but we didn't. That's going to be what goes down there. Does that make sense? Kind of, sort of. Not that different. If you understand how we got there, it's not that different than what we did in the past. We're just adding a little bit of a wrinkle. We can't use the point of equal area anymore. We now have to take into account the point of equal load. Okay? Point of equal load. And we were actually doing that before. Whenever we did this previously, it was the point of equal load. It just happened to be that the Fy would cancel out in all of these calculations. So it was easier to think of it as the point of equal area. Okay? Now we have to not make it so simple, make it a little bit more complicated. Oh, there'll be some fun problems coming up where we have to do ones like this. Okay? It's coming up. And remember again, when you have something that's, you're trying to find m sub y, how do you do that? You just check. You check at the critical areas. You say, well, what moment does it take to cause this to yield? What moment does it take this to yield? This to yield? This to yield? Wherever I have changes in cross-sectional area, wherever I have changes in cross-sectional Fy. Okay? And you find the lowest one, and the lowest one wins. Okay? Okay. See ya.